This discussion is about stoichiometry and its importance. Hopefully it'll give you a quick little overview of what we need to do to convert grams to grams and grams to moles and so forth. What are these calculations? Well, chemical equations can be used to relate the masses of chemical reactants and products. And of course, the most important thing is balancing the equation for the reaction. The coefficients are the number of moles, and that will lead us to the correct ratio between the reactants and the products. Then convert the known mass of the reactant or product to moles. Use the balanced equation to set up the appropriate ratio. Then use the appropriate mole ratios to calculate the number of moles of desired reactant or product. Convert from moles back to grams if required by the problem. So, here's an example. Consider this reaction. P4 plus 5O2 yields 2P2O5. If 6.25 grams of phosphorus is burned, what mass of oxygen does it combine with? Well, let me show you how to do this particular problem. What mass of oxygen, so how many grams of O2 are 6.25 grams of P4? Notice the wording in the question says phosphorus, but if you look up at the question, it says P with a subscript 4. Make sure to use the correct compound or molecule when writing down the information, because the next step, which is going to be from grams of P4 to moles of P4, if you just saw the word phosphorus and thought P and looked that up, you would have the wrong formula mass. In this case, it's 124. And of course, units cancel. And then we go from moles of P4 to moles of O2. For this, we look at the balanced equation. You notice in front of P4, there's a 1, and in front of O2, there's a 5, and that's what I put in front of the mole ratios. And then finally, mole of O2 to gram of O2. 1 mole is 32 grams, because oxygen is 16, and I think the answer, oops, it's showing up underneath there, is 8.07 grams. So that's how we calculate using stoichiometry. Let's look at this particular question. Here we have some equations, and it says methane, CH4, reacts with the oxygen in the air to produce carbon dioxide and water. It also says ammonia, NH3, reacts with the oxygen in the air to produce nitrogen monoxide and water. Now, writing balanced equations is pretty easy. You have to decode it. So methane is CH4. It reacts with the oxygen in the air. Remember, oxygen's diatomic. And it produces carbon dioxide and water. Okay, that's the unbalanced equation. And then with coefficients, you should get that. Remember, the number of carbons, hydrogens, and oxygens has to be the same on the left as on the right. And hopefully I did that correctly. There's 1 carbon on the left and 1 on the right, 4 hydrogens on the left, 4 hydrogens on the right, and 4 oxygens, and then 2 plus 2 more is 4. The next one, ammonia, NH3, reacts with the oxygen in the air to produce nitrogen monoxide and water. Well, it looks like it's going to be a little bit more tricky. NH3, O2 again, produces nitrogen monoxide. Remember, this is the prefix naming system, and neither have any kind of subscript. So 1 nitrogen and 1 oxygen, and of course, water. Okay, balancing back and forth, I think we'll end up having an odd number of oxygens on one side. So let's see if this works. And that would give us 10 oxygens. This is 4 oxygens and 6, which make 10. 12 hydrogens, 4 nitrogens, 4 nitrogens. So that's the balanced equation there. Now the same question is used, and now they're asking about what mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen. This is a pretty interesting question. I like it because it uses information from one equation you then have to solve, and then you have to use that information to actually answer the question, in this case, what mass of ammonia. So eventually, I'm going to put this up here, we want to know how many grams of NH3 would we produce from the same amount of water as 1 gram of methane reacting. So that means, I guess I'll put this here above the methane one. How many grams of water are they talking about in that 1 gram of methane? How much could we get out? Now, what I did, I'm going to go from grams of CH4 to moles of CH4, and that is 16. Then I'm going to go from moles of CH4 to moles of H2O. And that's 2 to 1. And I got that from my balanced equation, which was on the previous slide. Then finally, moles of water, 2 grams of water, which is 18, I get 2.25 grams of water. That's the amount of water they're talking about in this particular question. So I'm going to put the 2.25 grams to answer this original question that I wanted, which was this one right here. And now I can just solve this, and this is of water. Got to make sure sometimes to write the correct units, because sometimes you might put the wrong coefficient if you don't, or the wrong formula mass. And that goes to moles. And that's still 18. Moles of water to moles of NH3. That was 4 to 6, according to the previous balanced equation. And then moles of NH3 to grams of NH3 is 17. And the final answer is 1.42 grams. That's a pretty interesting question because it had you use one thing to get something else. Remember the idea of limiting reactants. Limiting reactants actually limit the amount of product being produced. It's the reactant that is consumed first and therefore limits the amount of products that can be formed. Sometimes you're given information and you have to solve that to figure out which is limiting. Determine which reactant is limiting to calculate the amount of products formed. Here's an example. Methane and water will react to form products according to this equation. The amount of products that can form is limited by methane. Methane is the limiting reactant and water is in excess. So here's a good example. Which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolized by this equation. 2H2 plus O2 yields 2H2O, symbolized by the equation. And our choices are A, B, C, D, or E. So for part A, 2 moles of hydrogen and 2 moles of oxygen. So if you think about them separately and how much water they could produce, we can then see which is going to produce the most. Alright, 2 moles of hydrogen, here it is here, it will produce 2 moles of water because it's a 1-to-1 ratio. The next one, 2 moles of oxygen. If I had 2 moles of oxygen, it would produce 4 moles of water. But, because it's a limiting reactant problem, we always choose the smaller answer. So, part A will actually only produce 2 moles of water. Let's see what B can do. 2 moles of H2 still produces 2 moles of water. 3 moles of oxygen, however, alone, just looking at that one factor, can produce 6 moles of water. Well, again, we have to choose a smaller answer. So it looks like A and B can both produce 2 moles. All right, moving on. Part C, 2 moles of hydrogen can produce 2 moles of water again. 1 mole of oxygen can produce 2 moles of water, pardon me. Again, it doesn't matter, the answer is still 2. And if we notice, we can go through this again. 3 moles of hydrogen would produce 3 moles of water. 1 mole of oxygen can produce 2 moles of water. And in that case, 2 is the smallest of the 2 choices. And if we scan the answers to A, B, C, and D, you can see they all produce 2 moles. So therefore, I think, yep, the answer is each produce the same amount of product. We can't simply add the total moles of all the reactants to decide which reactant mixture makes the most product. We must always think about how much product can be formed by using what we are given and the ratio of the balanced equation. Now, here's a good question. You know that chemical A reacts with chemical B. You react 10 grams of A with 10 grams of B. What information do you need to know in order to determine the mass of product that will be produced? Well, of course, we need to know the limiting reactant, and that one is the one that's going to give us the smallest products. We also maybe need to know the identity of A and B and their molar masses, but let's see what we can do. So here's the question. Now, it says you react 10 grams of A with 10 grams of B. What mass of product will be produced given that its molar mass of A is 10 grams per mole, B is 20 grams per mole, and C is 25 grams per mole? They react according to the equation A plus 3B yields 2C. We also have to remember that you need a balanced equation to see how those things are related to be able to calculate which one's limiting and how much product will be produced. And you can see those are the things that go together. 25 grams per mole relates to product C. So, whoops, let me go back. And we're actually going to solve this particular question. I thought there was going to be another space, so I apologize. So, what I tend to do when I see a question like this, instead of determining which is the limiting reactant first and then proceeding, which is perfectly valid, and oftentimes textbooks like that, I tend to solve these equations twice and choose the smaller answer, because it's a pretty simple stoichiometry move, and it actually takes less thought for me. So I will show you what I would do. I would want to know how many grams of C could be produced from just the 10 grams of A. I'm going to do the same thing with 10 grams of B. So I'm just solving twice for substance C. When I do, grams of A, this is 10 grams, and the mole ratio is 2 to 1. I'm trying to go quickly, and I'm not actually putting the units too much. This is the mole to mole, and then the mole to gram of C. I'm going to do the same thing with substance B. Different mole ratio this time. So mole, and still the same formula, mass for C. When I work it out, let's see, I get 50 grams of C, and I get 37.5 grams of B. So 37.5 grams is the maximum amount I am able to produce, because there was a certain amount that was unable to be produced because I didn't have more B. B is the limiting reactant. Now if I could determine that B was limiting, I would simply only do one equation. But as I said, because I think this stoichiometry is pretty straightforward, it's just as easy to do two quick equations and see which one is smaller. Now back to this one. Consider the following reaction. P4 plus 6F2 yields 4PF3. What mass of P4 is needed to produce 85 grams of PF3 if the reaction has a 64.9% yield? Now here's a really good question, because 64.9% yield is about percent yield. And I know we talked about that in an earlier video. And that's an easy calculation. But here it is kind of slipped into another kind of question to make this one a little bit more exciting. So if you were to just do the problem, meaning if you said how many grams of P4 are 85.0 grams of PF3, using the formula mass of PF3, the mole ratio, and the formula mass of P4, pardon me, I believe you would get 29.94 grams. And I'm not going to do that out for you. I think you can do the 3 parentheses and hopefully agree that it's 29.94. Now that answer, however, is only 64.9% yield, because it says that's what's produced. So therefore, if you want to know what mass gets you that, you would have to do a quick little calculation. In other words, if 29.94 grams is 64.9% yield, then how many grams would be 100% yield? And when you do that, you get 46.1 grams of P4. That's the actual accepted answer. You could also, if you wanted to, instead of starting out with the 85 there, you could figure out what 100% would be. How many grams would be 100%? So if you started out with, instead of 85, you could have done 130.9 grams. That would be 100%. And then you could answer the question. You too would get 46.1 grams of P4. So it's a good question, and it integrates two concepts that we don't normally put together, or we certainly didn't in the intro class. And that's just the beginning of how some of the questions in the AP will prove themselves a little bit trickier, because they try to kind of mix and match different concepts. Hopefully that will help you as we do more complex problems in class.